Well, thanks. Hi, everyone. Today I'm going to talk about the magic of music matching. That's a mouthful. A little bit about me. I do some stuff and I work for OpenValue. And you can find me online on Twitter or on my own website. So, why did I get into programming? For me personally, it was a way to play games. When I was younger, I was allowed to play with my father's first PC. And the only way to really get games was to go to the library and get books like this. And in these books, there were pages filled with source code. And this source code you could type into your own PC, in your own computer. And then finally, if everything compiled and you didn't make any typos and the syntax was correct, you could actually play this game. For me, this was the main reason to get into programming, basically just to play basic games. And this kind of made me understand how things work. I didn't really know how to program. There were some tutorials in those books as well. I followed those. But just by making mistakes and trying to fix them, I learned how to program. But still, software sometimes has the magical moments. The first time I went from a text program to something that could display images, that has logos and photos of people on my computer. This felt like magic. I had no idea how I would program something like that. Because up to then, the only games I made were text-based games. The first time I navigated a 3D world, that was something new. When I played Wolfenstein or Quake, I had no idea how you could possibly program something that moved in 3D. Or the first time a computer spoke to me with a human voice. So the first games that had some voices in it was really magical to me. I had no idea how to make that. Or the first time you took a picture and the computer recognized characters using OCR. Or voice recognition. Initially it was utter crap. Only the last couple of years when Alexa came around, things started to become better. But how do you write a program that listens to your voice and knows what you're saying? Or Google Earth, the first time you found your own home on Google Earth. That was very cool. And maybe one of the last times I had this was when I first used Shazam. By that time I was already a professional programmer, but I had no idea how you would start to make something like that. So, story time. This all happened about 10 years ago in Maasluis, where I currently live. And I was drinking beer with my friends in the local pub. And one of our friends got out his iPhone and he told me, look at this app, this is very cool. And he started Shazam and he put his phone up in the air and there was music playing. The phone listened for a while and then it told me the name of the song that was playing. My mind exploded. Like how does this work? How do you write a program that listens to a song and tells you which song? That's something only humans can do. So the next morning, a little bit hungover, I woke up and I have to know how this works. So my goal that entire weekend, find out how this works, recreate this. So the first thing I did, obviously, was Google. I'm a Java programmer, so I want to do this in Java. How do you listen to a microphone in Java? And it turns out this is actually pretty easy. There is a Java Sound API, and you can access the microphone. And the first thing you need to do is to define an audio format. And this audio format contains a couple of things. It has a sample rate. It has a sample size in bits. The amount of channels. Is there one microphone or do you have two channels? Is it stereo? Is the information signed and is it big or little endian? And you create this audio format and then you can use this audio format to access the microphone, which is rather easy. There's a target data line and in this target data line you can open it and you can start it and then information from the microphone starts pouring into your Java program. It's that easy. So the main thing is there's an audio system, and you can get a line from the audio system, and with the given input data, it will set everything up, and then you get the target data line, which is the raw microphone data. This data comes streaming in, and we want to store it. So in this case, I created a byte array output stream, and I would read from this target line, calling the line.read method, and I put everything in a byte array buffer. So at a later point, I can use this underlying byte array to just look what the microphone is giving me. So 2 hours later, finally time for breakfast. I had this feeling, I nailed it. I'm halfway there. I already get all the data from a microphone, so I'm nearly there. So then I opened up the data. What does a microphone actually give me? And this is the data I got, like some numbers. But what do these numbers mean? How does a microphone even, how does your ear even work? How does everything work? Like, everything crumbled. So, looking at this data, I didn't get any smarter. But then I tried to plot this as a graph. So I opened Excel, and I plotted the numbers. This looked familiar. If you've ever
We have a little bit of a problem. Well, the battery is empty of Roy's microphone, so we'll change that quickly, and I think he's back.
I think I'm back. Where did you guys miss me? Where did we get to?
I heard you perfectly.
Go into the chat. Tell me where it went wrong.
Just the last minute, I heard.
Okay,
so,
just the last minute.
Yeah.
So let's just start from breakfast. I had breakfast and I thought I nailed it. I got all the data from the microphone, and the only thing left to do was just match it up and see which song it does. So then I started to look at the data, and I got all these numbers. And these numbers didn't mean anything to me. So what does a microphone even do? What data do I even get in my program? So I tried plotting it in Excel. And if you plot the numbers in Excel, this is what you end up with. And this, to me, was recognizable. If you ever used an audio program or an audio editor or even a video editor, audio is often represented as this, as waves. When you're silent, it's a solid line. When you make noise, it goes up and down. So, it's time for some biology and physics. Sound is basically pressure. So, if you speak or something happens, if you hit your hands, the molecules are moving and they bump into each other, and this pressure wave eventually reaches your ear. And inside your ear, there are a lot of small canals, but there's a small eardrum, and this drum moves side to side with the molecules in the air. And your brain perceives this as sound. And a microphone basically works with the same principle. There's also a small membrane in this microphone, and it also moves side to side. And these numbers that we're getting from the microphone is actually the position of this membrane. So it can go positive or negative. And that's also what you see in the graph. It goes up and down. That's what a microphone does. Now you can also understand what the sample rate does and the sample size does. So if you have a higher sample rate, it just means you get more of these positions. So you get more precision. The second thing you can change is maybe get 7 bits of data or 8 bits of data. So it's just more precise on where this membrane is. because there's more numbers to put in. So these are two things you can use when you're using a microphone and tweak to get a better performance. Turns out though that the positions are basically useless because our ears do the same as a microphone to detect waves, but our head only hears frequencies. So we have to turn this around a bit. If there's a single low frequency, there's a single big wave. And we hear one single frequency, one tone, like one single tone. But actually, it's moving up and down all the time because it's still following this sine wave. If we have a higher frequency, it just moves up and down more frequently. So it's a higher tone, but to our mind or to our ears, it's moving side to side, but we hear one single frequency. It gets even weirder if you combine like a very low frequency and a high frequency sound. You get some signal that's completely messed up, but our head just hears two distinct frequencies. So just measuring the position of this wave doesn't really tell us a lot, because if you want to talk about what we're hearing, we actually need the frequencies. Luckily, there's a simple way to transform these waves into frequencies, and that's done using the Fourier transformation. Stuart Riffle explained it on his website. His website is no longer online. Luckily, I saved his explanation in his files. But his basic idea is, if you have some audio or some signal, you can look at this as having a bar and a dot moving up and down, which is our membrane. And the image we're plotting, we're just going like this while doing this. If you want to do the Fourier transformation, instead of doing this, we do this. We rotate the axis and then go up and down. So for example, if we take this signal and we rotate it at about 10 hertz or something, you'll get a picture like this. It looks like a spirograph, but you're moving around, and it's basically based around the center. If we would do the same thing, but instead of rotating at a frequency of 10 hertz, we would choose a frequency of, I don't know, 3 hertz, we could end up with an image like this. And you can see that it's no longer center, it's being pulled off center. And the reason that it's being pulled off center is that the frequency 3 hertz is actually in the signal we originally had. So imagine that we are rotating at the same frequency as a sine wave, and we go all the way to there, then we go back, and then we go all the way to there again. So this tells us something. If we do this at 3 hertz and it gets the center is being pulled from the center, that means the 3 hertz signal is actually in there. If we would remove the 3 hertz signal from the original signal and then plot again, it would jump back to the middle. So that's kind of how the Fourier transformation works. It's just rotating and then seeing if that particular frequency is in the audio sample. And if you look at the Fourier transformation formula and you know this information, you can spot all these little things. So to find the energy at a particular frequency, we spin, which is e to the imaginary I, which stands for spin, the signal, which is x, around a circle, which is 2 pi, at that particular frequency, so we're using the same frequency, and then we average a bunch of points along that line. We take numbers 1 to n minus 1, and we divide it. So, cool, now we know how the Fourier transformation works. Do I want to program this? No. So I went to Commons Apache, and there is a fast Fourier transformation. We can just use that. So, listen to a microphone, store all these positions, throw it into the Fourier transformation, and then you get the frequencies. Problem solved. Turns out there's still one big problem, because if you do the Fourier transformation, you lose track of time entirely. It is like if you have a sample of 4 minutes, for example, a song by U2, 4 minutes long, if you do the Fourier transformation and you look at the results, you get all the frequencies in those 4 minutes. It's like the band playing every song at every note of the entire song at the same time. You need the time aspect, but because you do the Fourier transformation and you squash all these waves into the frequencies, you no longer have any idea when these frequencies are happening, which is kind of important if you want to know which song it is. So I was a bit devastated. It was getting close to dinner time. I was looking out of the window, and suddenly it hit me. Windows could be used to solve this problem. We can use windowing. What you do in windowing is, if you have this entire big song, you just take a couple of seconds, or even smaller, you do the Fourier transformation, and then you slide the window a little bit. Then you do the Fourier transformation on this part, and on this part. Now you do lose a little bit of timing information, because it's still a sample being squashed to the frequencies, but we know when it happens. So this kind of solves the problem. In code, we could do the following. We take out the bytes from our microphone, and then we slice it into a couple of slices, and we move this window along, and we do the Fourier transformation, which is just Commons Math Fourier transformation. And then we have the results. Then we have the frequencies over the song. A better way to do this is not jump over, but just slide a little bit at a time. So there's even more overlap, and you get more time information with having a larger window. If you would combine everything, you end up with this, and this is a spectrum analyzer. So I wanted to create Shazam. First day, I created a spectrum analyzer. And there's a small demo. Headphone warning. APHEX Twin is a DJ who makes music, but it's not really music. Sometimes he just makes a lot of noise, but he hides information in his songs. So this YouTube movie is from one of his songs, and if you would play this song to a spectrum analyzer and you look at the information, this is what happens. There's a small head hidden inside the song. So if you would play this song against a spectrum analyzer, it will show you this image. This, to me, was very useful because I knew this song would produce this image. So the only thing I needed to do was do my Fourier transformation on this sample, plot it, and it should look something like that. And after a bit of tinkering, I created the following. It's not perfect, but you can kind of see the face in there. And even the lines on the side going up. So I knew my code, the Fourier transformation was working, the display not so good. So I'm probably not using the correct logarithmic scale to display this, and my microphone might not be good enough. The above example was made using a professional spectrum analyzer. This was just a couple of hours of Java code. But it seemed to work. So, time to go to bed after the first day. A small recap. What have we learned? Sound is just basically vibrations. Microphones and ears do very similar things. They just move side to side. And accessing this data in Java is actually really easy. There's a whole sound API you can use. There's a problem with the time and the frequency domain. So in the time domain, we have these vibrations, but we want to have the frequencies. But if you just look at the frequencies, you forget all about time. We can use the fast Fourier transformation to actually turn time into frequency. We use windowing to slice everything up and get frequency information and still have a little bit of time information. And if you put all of this together, you get a spectrum analyzer, which was cool, not what I wanted, but it's what I got. So the next morning, got up a little bit sooner, time to do fingerprinting. And this is actually the missing step to go from a spectrum analyzer to having something that works like Shazam. So I took a random song and I put it in my spectrum analyzer, and this is what came out. And then I did the same thing again. This came out. And these images look very similar. There are obviously differences. There's different background noise. But this is something we could work with. And this is also how Shazam does these kinds of things. It takes this spectrogram image. In my case, I divided it into frequency bands. So the bottom is very low frequencies, and on the top there are high frequencies. And you go through them in time. And I look at the most loud frequencies. So for each slice, I take the frequencies that are loudest at that particular time. And I do this for the entire song, and then you end up with the red dots. And if you would overlap these two things, so that's the code we need to write, and then we can look at the difference between these two things. You can see there's a lot of overlap. And this is actually what Shazam does with the matching. So we have all these slices, which have a lot of frequencies in them. And then we pick the loudest frequencies across these bands, giving us the red dots. Now we compress everything down to just 64 bits. And then we store this in a single long value. So in my case, you can see in the top there are these 4 loudest parts, which is the 1, 1, 1, 1. Then there's not so much loud parts, and then there's 1, 1, and another 1, 1. So this slice of frequencies is actually encoded as a single long value, and the entire song is just a list of these long values. So it makes this fingerprint for a particular song very small. And there's another trick we can use, which is doing hash lookups. So how do I create a library of these fingerprints? So this was back in 2010. I didn't have Spotify at the time. I had my huge MP3 collection, which everybody had. So I used these 3 tools, which plug into the Java Sound API, and then you can decode MP3 files and access them the same way as we could access the microphone. The only thing left to do was actually harvest everything that ends on .mp3, and this was my 2010 code, which I would no longer write like this. I would use the new I/O, which is much, much, much smaller. Go through my library, everything that ends on .mp3, capture the audio, and create this list of longs. So now I have 3,000 plus fingerprints. I have a method to capture these fingerprints from a microphone. The only thing I need to do is listen to the microphone, get these fingerprints, and look in my database which one it is. That seems pretty manageable. So if we record and we get the following fragment, these longs, I do a hash lookup. And hash lookups are very fast. So my entire database of all the songs is just a collection of hashes with a single long value. And for each thing I record, I can do a single hash lookup and get all the matching songs. And if I do this, and I can even get the offset into the song, which is also important. So I do this for my recording. I do a hash lookup, and I look at all the matches. And if a particular song jumps out, then I say, well, I've got a match here. So, for example, we do 100 hash lookups, and 80 of them give a particular song. That's more than enough to say it's probably this song that's playing in the background. So we also have some quality measurement here. And just in time for dinner, I had my working Shazam clone. And I'd like to ask Gerrit to do a pub quiz. So we can actually demo this and do a pub quiz at the same time. So first, I'll stop this. And I'll run my matcher. And next, I've got my I've got my computer. At the moment there are 500 songs from the Rolling Stone magazine. The top 500 songs are indexed on my machine. There are actually 17 songs missing, which I couldn't find or couldn't download or it wouldn't process. And I've got the playlist on my phone. So Gerrit, are you ready to do this? I'm going to play a song and let's see who's faster, my computer or you.
Camouflage, Beastie Boys.
Sabotage.
Sabotage, sorry.
But the computer was a little bit faster. Let's do the next one. Still hasn't got it. You can still win.
Very known song, but I don't know the title.
The computer knows it. The computer knows it.
Yeah.
So next one.
Kiss, Prince.
Yes. It's 2-1. It's in the top 500. I can't help it. But my computer is telling me that's Jackie Wilson. You already recognized it. My computer has it. Sorry.
I don't know.
The Shazam clone has it. Sorry. Come on, something you can know. This one, you know this one. You know this one. The computer still has it, doesn't have
Madonna, Life is a Mystery, Like a Prayer.
Like a prayer, yeah. You got this one.
Yeah? Okay.
Yeah.
So it's 10-2.
Yeah. So it actually works amazingly well. It can recognize the songs and I can just play some song. And if you give it enough time, I can even at the same time talk and often it will just recognize it. Yeah, I'll stop. So this is the first demo I would like to do. The second demo I want to do is taking this concept and doing even weirder stuff. So in this case, I've got my program here. And right now, it's actually listening for a particular movie soundtrack. And in this case, it's the movie Rush. Rush is a movie about Niki Lauda, Formula 1. It's a cool movie, and I happen to have the MP3 file of the entire movie. If I now go to YouTube and I look up some random scene from the movie, pick a number, 1, 2, 3. 3, the third one. So now I play this particular sample. And at this moment, I can stop my phone because my computer not only recognized this, it can continue playing it. So right now it's playing the sound at that particular moment in time. So not only can you recognize songs, but you can also recognize where you are in a song. And you can actually match this up, which is very useful in some cases. So let's go back to the presentation and look at some cases like movie alignment. Can you do duplicate song detection with this? Absolutely. This is the first thing when I had my entire MP3 collection. I ran this algorithm on all my songs, and it had a lot of songs that were on 2 albums or on collector's albums, and even some songs that had the original version and the live version, and it would say this is the same song in about, it's 90% the same. So you can totally use this to detect songs. Another idea I had, which I haven't implemented yet, is the alignment of subtitles. So if you download a movie and you download subtitles in an SRT file, they have a timestamp. But this timestamp references one particular movie. And sometimes the movie just starts later and then the subtitles don't align properly. But if you would use the audio track to sync this up, it should always be perfect. No matter where you are in the movie, it should detect it and the subtitles should work. Because you can detect duplicate songs, you can also use this for copyright infringement, and I'm pretty sure YouTube is using the same thing here as well. Speech recognition, I don't think you can use this particular technology to do speech recognition. So, recap of the final day. You use fingerprinting to find your match. Hashes are incredibly fast, so even if you have a database of millions of songs, because you're doing a hash lookup, it's very direct, and you can distribute this over a lot of machines and get your results back. So this scales very easily, and that's probably why Shazam is so incredible. It's very cool technology, but it's not impossible for humans to program something like this, which I felt like it should have been. There's still loads of room for improvement in my code. It's basically a couple of weekends of work, and then I dropped it. But yeah, I'm pretty sure if you give it enough time, and yeah, you can make this much better. But in the end, after 1 weekend, I had a working music matcher, and it can beat you in a pub quiz. So that's about it. Are there any questions, Gerrit?
Yes, there are.
Awesome.
First of all, there are lots of memories from different people about elementary school and typing codes for entire days and recording programs from radio. Yeah. But there are actually a couple
I never did that.
No?
No. I never had my tape recorder actually listen to... I know it exists, but I've never done that.
Would be interesting if you could write the code from listening to the recording effect.
Who knows?
Yeah. A question. Got a question. Where is it? Could you potentially also recognize individual singers in a song?
Ooh, I don't think so, because it looks at the whole of the song. So it looks at all the particular things that are loud and not loud, and it creates basically an image of that, and that's what it matches. So maybe you could listen to the frequencies and the harmonics and maybe detect if it's... I don't think so.
No, okay.
You could, but I don't think so.
The other question is not about the singers, but maybe you can say something about that. Can you recognize birds by their sound?
That I know these applications exist, that you can just hold it up. I think that could work better, but only if they play the same songs. And some birds do, but most of your birds sound differently. Maybe. Yeah. Give me a big data set and I'll try it.
Okay. So for the one asking the question, just deliver a big data set and you'll get the answer
find me on Twitter.
Later on. Okay, let's see if did I miss any questions? I don't think so. Lots of reactions of people who think it's awesome what you did, so that's positive.
It feels awesome, and it kind of takes the magic away. But yeah, it's still when I open this app and I can just do it again. It just, for some reason, I still like the fact that it works, and it still amazes me that you can just play some song and it matches. Yeah. This is the perfect toy.
I'm so happy to be here tonight.
Blues
Yeah.
Brothers.
So glad to be in your wonderful
Or is
city.
this
Solomon Burke.
that's the original version probably?
Yeah, it doesn't work. Next. Yeah. So it just it is magic. Any other questions?
No other questions. No other questions.
Okay. Let's
So,
wrap it up.
yeah, many thanks.